Hi everybody, time to go through some answers to this even more nuclear reaction practice worksheet to hopefully help you get ready for Tuesday's quiz. So the first one here, it says calculate the amount of energy released in kilojoules per mole when uranium-235 undergoes fission to form tellurium-137 and zirconium-96. We need an equation to start with. So we've got our uranium-235, mass numbers 235, atomic number 92, forms tellurium-137, atomic number 52, and zirconium-96, atomic number 40. Now if you take a look at the mass numbers 96 and 137, that's 233 for mass, and we have 235 on the left, so we have a mass of 2 left over, so we're going to have 2 neutrons that have to be released. It kind of leads you to believe that there's going to be a neutron, considering you're given the mass of a neutron, so it kind of leads you to believe that that's the third product. To find out the amount of energy released, we need to figure out the mass defect for this reaction. So we find the mass of the reactants and the mass of the products and find the difference. So uranium-235 has a mass of 235.043915 AMU. And if you add up the masses of tellurium, zirconium, and 2 neutrons, you get 234.851063 AMU. If we subtract these two values, you get a mass defect of 0.192852 AMU. Remember, technically speaking, this is a negative value because we know energy is going to be turned into, mass is going to be turned into energy, so we know this is actually a negative amount of mass as it turns into the joules released by the reaction. Next up, we can use our E equals mc squared equation to find the amount of energy. So we've got E equals 0.192852 AMUs multiplied by our conversion factor to change it to kilograms, 1.6605 times 10 to the minus 27th kilograms per AMU, multiplied by the speed of light squared in meters per second. Value comes out to 2.88208 times 10 to the minus 11th, and that would be in joules per atom of uranium. We want this thing in kilojoules per mole, so we need to divide it by 1,000 first to get it into kilojoules. So you got 2.88208 times 10 to the minus 14th kilojoules per atom. And if we go ahead and multiply by Avogadro's number, 6.02 times 10 to the 23rd atoms of uranium per mole of uranium, you get this thing into kilojoules per mole. It comes out to be 1.73501 times 10 to the 10th kilojoules per mole. Next problem. We're looking at calculating the amount of energy in joules released when 1 mole of H2 fuses with 1 mole of H3 to make 1 mole of helium-4. And there's one more product we need to figure out. So starting with the reaction, we've got hydrogen-2, also known as deuterium, fusing with, so coming together with an atom of tritium, H3. We know it's going to make helium-4. We have one more product that we need to come up with. Now if you look at the mass numbers, 2 and 3 adds up to 5 on the left, so we need a mass number of 1. And our atomic numbers on the left are 2, atomic number on the right is 2, so this can't have any mass there, or any atomic number there, so what particle has a mass of 1 but is not a proton or an electron? Well, it's a neutron. Next up, we're going to look at the masses of our reactants and our products. If you add them together, you got 5.030131 AMU. And over here you got 5.011267 AMU. You see that the mass goes down a little bit, so we're going to subtract to get our mass defect. 0.018864 AMUs. There's your mass defect. It's always good to label it if you can in the problem. Kind of helps show where you're going and where you've come from. At this point we can find the energy by doing E equals mc squared. Our mass is 0.0818864 AMUs. Conversion factor. Speed of light squared. The answer comes out to be 2.8191 times 10 to the negative 12th. That would be labeled joules per atom of helium that's formed, or it's per atom that reacts. So this is per atom of deuterium or per atom of tritium. Now, since our answer wants when 1 mole of deuterium fuses with 1 mole of H3, we need to change this per mole. So 6.02 times 10 to the 23rd atoms for every 1 mole in an atom. And again, this could be talking about atoms of anything here. It's a 1-to-1 to 1-to-1 ratio. All of the coefficients in front of all of our reactants and products they're all ones. So this is per 1 mole of anything. Multiply that out, and you get 1.6971 times 10 to the 12th joules per mole. Next up, thorium-230 decays by alpha emission. Calculate the energy released in kilojoules when 0.68 grams of this thorium isotope decays. So we need a reaction first of all. So thorium-230 is going to decay by alpha emission, 4,2 in a helium nucleus, which means that our mass number up here needs to be 226. If you look up the atomic number of thorium, it's 90. And so there's 90 protons on the left. We already have 2 protons on the right, so we need another 88 protons on the right, which means that our atom needs to be radium, Ra. Next up, we can look at the masses. The reactants masses 229.9837 AMUs. Our products mass is 229.97725 AMU. Subtract our masses to get the mass defect. You get 0.00645 AMUs. Mass turns into energy, and this reaction releases energy. So we can go to our E equals mc squared equation. Mass is 0.00645. Conversion factor. Speed of light squared. Energy comes out to be 9.64 times 10 to the negative 13th joules per atom of thorium. Now, the answer for this problem, first of all, wants kilojoules, and secondly, it's using 0.68 grams of thorium. So I'm going to start with this number I just came up with, this 9.64 times 10 to the negative 13th joules per 1 atom of thorium. And I'm going to train track this thing until we get to the answer. I know that there are 6.02 times 10 to the 23rd atoms of thorium in a mole of thorium. And then 1 mole of this thorium isotope, it told us in the problem, is 229.9837 grams. We're working with 0.68 grams of thorium. which I could have started the problem with that number since it's not a conversion factor, but it works out here. Cancels all our units. And last but not least, we want to change our joules to kilojoules, so 1,000 joules for every 1 kilojoule. Joules cancels out, atoms of thorium, moles of thorium, grams of thorium. So our answer is, rounding to 2 significant figures because of the 0.68, I've got 1.7 times 10 to the 6th kilojoules released. And this is really a good point to go up and say released for all of these amounts of energy. Remember, we stopped writing the negative sign for the mass defect, but we're just remembering that these reactions are all giving off energy. For the last problem, the screen capture program that I'm using only allows me to record 15 minutes maximum per video. So I'm at 11 minutes now. I'm not going to be able to finish number 4 on this video, so you'll have to tune in for a different video to get the solution for number 4.